Hello, everybody. Sorry I have to be out sick. Let's do a quick sum up from last time, and then I'll have a little warm-up problem for you to think about, and then I'll launch you on the big problem set for today. So the sum up from last time, we spent the whole block on this problem where we wanted to determine the average outcome from an experiment involving some number of steps. So we had a particle that was going to diffuse for 3 random steps, and we wanted to know what was its average displacement. And here's sort of how we thought about that. We want to display a table of values, but the difficult part was figuring out what number goes here, because this is going to be the result of 10,000 experiments, because we can't know what the average is unless we do the experiment lots of times. So what was the experiment we were trying to run? The experiment was take 3 random steps and see what the displacement is. And then you add all those displacements up and divide by how many. So where we ended was this way of breaking the solution apart into pieces. We had a method called do experiment, or whatever you want to call it, where we're going to take a number of steps, step at random, and then calculate the distance. And then we're going to run that method over and over and over again. We're going to run it 10,000 times. And this method is just about calculating the average outcome. So we don't actually take steps in here. We just get the results, add them together, divide by how many. And that's enough to give us one of these numbers in the table, specifically whichever number corresponds to the average displacement for the steps we're taking. But then we need to run the calculate average method over and over and over again, once for each row in the table. So if you need to, you can pause this slide and look at it. But my question is, what would you need to modify here if we wanted to change the problem a little bit? Let's say I wanted to roll n 6-sided die. So n is going to be a number that changes. So maybe I'll roll 2 6-sided die, or 3 6-sided die, or 17 6-sided die. And I want to find the sum of all of the dice that have even numbers. So I roll 17 dice, I look and see what's even, I add all those evens up. I want to know, on average, when I do it over and over again, what's that sum going to be? So why don't you think about each part of this? What needs to change? Does anything in the table display need to change? What? Does anything in calculate average need to change? What? Does anything inside do experiment need to change? What? Okay, pause the video. Really think about it. You're going to learn more. Okay, so here we go. The only thing that needs to change is inside the do experiment method. Everything else is exactly the same. So inside do experiment, instead of looping for the number of steps we want to take, we'll loop for the number of dice we want to roll. And then inside, we'll generate a random number that corresponds to the number on the die. And then we'll check if it's even. And if it's even, we'll add it into a sum. And then we'll return... Oh, is it the number that's even? Sorry, hold on. Okay, there we go. So we'll roll and we'll add the value of even, and we'll return the sum. This calculates an average, and that doesn't need to change. Last time, the average was the average outcome from our experiment, which was the average displacement. Here, the outcome from our experiment is a sum, and so this is going to find the average sum. So it still does what we want. And display the table also still does what we want. So even just a very small change has now adapted this to be appropriate for a new problem. Okay, last thing before we do the problems. What if I want to know the probability of a certain event instead of the average end result? So here's what we would need to do if we wanted to figure out the probability of n dice all showing even numbers. And that would be an easy thing to calculate theoretically, but let's use this as a learning example to see how would we do it experimentally. So the way you calculate a probability is you run a bunch of experiments, but this time you don't add the outcomes. You check to see, did the experiment do the thing that I'm interested in? So here I'm interested in, are they all even? So if all of the die were even, then I'll add to a count. And then I'll see how many of the 10,000 ended up the way that I was interested in. And that gives me the probability. That'll give me the percent overall out of 100 of getting the outcome I wanted. So inside the experiment, I'm still going to do the same experiment where I'm rolling n dice. But now I want to check were all of them even, yes or no? And so I'm going to output a Boolean. And then here, I'll just check, was the output of my experiment true? Was it successful? Did it do the thing I want? And if it was, I'll count it. And then at the end, I'll return this count over the total number of experiments. So here's the two patterns. This is calculating the average result for something, where over many trials, we add all the things up and divide by how many. Here's the probability of something, where over many trials, we check if the results passes some test for being the outcome we want. And if it does, then we'll add to a counter, and we'll divide by how many. All right, so here's the timeline. Yesterday, we finished the diffusion problem. So if you haven't finished that, you should definitely spend no more than about 5 minutes and turn it in. I'm going to show you a document with lots of problems, and there's going to be 2 required ones and some bonus ones. Everybody should start off with the problem called Gambler's Ruin, and so you should definitely get to the end of that problem today. You also want to at least start looking at the testing fairness problem after that. Monday next week, we'll look at a couple of solutions, and you'll continue the testing fairness problem. And then Tuesday, Wednesday next week, you'll finish up all the problems. All right. Let me just show you what the problems look like. So this document is linked at the top of Schoology. I've got the 2 major patterns here. Here's the 2 required problems, Gambler's Ruin and do retakes make testing fairer, and they've been labeled easy and medium, although my judgment here is pretty subjective, and you might experience them differently. So you can click on it and go to the bookmark in the document to read the description of the problem. There's a lot of additional problems, and you can do them. You can do any of them. You could do none of them. You could do them in any order. They're marked by what I judge to be the approximate difficulty. If some of you are interested in adding back in the complexity of 3 dimensions and random directions, that's what this is about. So you can do the molecule diffusion problem in its original setting. There's one about the phenomenon of the hot hand in basketball, where if a player, the hot hand is when a player is more likely to get a shot after 1 or more hits. And so we could sort of like see experimentally, is that a phenomenon? This is a problem from the robotics team. This is how I think is the right way to think about strategy in robotics. Probability of a triangle, having children, some other ones. In machine learning, it helps to be able to think about higher dimensional geometry. And so this is a problem about how higher dimensional geometry, about how volumes and surface areas don't really work the way that your intuition says that they do in 2 dimensions and 3 dimensions. So you can think about that one. Probability of a non-self-intersecting path. Monte Carlo is a very famous counterintuitive probability problem. So there's a lot of them. And then in the more advanced ideas, if you're wondering why 10,000 experiments, what's the right way of figuring out the number of experiments? One right way would be to use confidence intervals. And so I sort of described that here. And then a traffic simulator where you can simulate why slowdowns occur. So lots and lots of things to dig your teeth into, probably more than anybody has time for. Use your time well today, please. I'm not going to add days on the end here. So definitely use your time well, use the TAs. Good luck.